Thank you. Yes, so this is a pretty different talk, I think, from most talks we've seen in this workshop, in that it's not actually on any climate models, although we do use them, but we'll see that further in the presentation. And to set the scene a bit, I want to explain first what this eWaterCycle project is about. So the idea in our project is that we're trying to get the hydrological community together to work together on building better models, which invariably means we have to start coupling these models. As you'll see in the next slides, we have quite a few models, and one of the interesting problems in hydrology is that the models are very different for different pieces of the world. So, for instance, the way water evaporates on a glacier is very different from a forest, and this really influences how models are built for this specific area. And in addition, there's also a lot of human influence going on, such as different constructs and also irrigation, and those also tend to really change the outcome of your model really on the model scale. So it's very directly, if you don't really properly model irrigation, also the type of irrigation used in a certain country, you will just completely fail to model the to produce any decent output of your model. So as a result, what actually happened in hydrology is that since of all these local problems, or this curse of locality as it's sometimes called, people also started really building local models. So really the scientists go in basically look in their backyard, see how the hydrological system works there, and try to build a model for this. And as a result, there's a lot of hydrologists that do their own measurements, that build their own model, which invariant of course leads them to also choose all sorts of different programming languages to do that, but also different libraries, and you see the different phases also. So whenever there's a new library comes out, this is not commonly picked up by everybody, so you get these very different versions of pretty much everything. And this also makes it very hard for this community to work together, since the models are so different. Although they in part have the same physics, actually the models themselves are so different that it's hard to work together. But in effect, they're all trying to do pretty much the same thing. Here's a very simplistic version of a hydrological model analysis, be it coupled or uncoupled. So what you see is that there's input data that goes in, which is also typically either local rainfall data, but also a lot of reanalysis products. Also climate model output is used here as the forcing, as it's called in hydrology. Then a model is run, implemented in any of these languages, and out comes river discharge, which is typically the thing that hydrologists care most about. Then these results are analyzed, and then some kind of conclusion is drawn from this. In this case, evacuate Zeeland if it starts to flood. So what you see is here's a couple of variants of the typical workflow that scientists are doing. You see they're all very similar, and so we kind of try to treat them in our system as variants of the same thing. Top left, you see people doing model development, which is very typical, and the thing that usually the modelers care about is how to improve their model to better fit reality. Top right, you also see people doing calibration on models, so they try to add better parameters. Uniquely to hydrology, there's a lot of parameters that describe different parts of the world. So these also needs to be added to the model, and they may differ for all the different models. Some people use the same system to also do decision support. And last but not least, if you do a model comparison, you of course also get this workflow, but then with a lot of different models. So since in our model we're really trying to get the modelers to come together and work together, and then through that get enough modelers on board that we can actually start to do coupled runs and also do inter comparisons, for instance. We actually built an explorer, which is a simple website where you can actually, on a globe, see all the different models that we have available, also with the different parameters, or maybe different resolutions, different forcings that they support, and that sort of thing. And then this is, I guess, very different from all of the couplers we've seen this week, in that what we actually try to do is leave the physical way the coupling is done up to the modelers. So for that, we actually expose all the models in Python, for instance, using a notebook system shown here. And then actually in this modeling system, the modelers can basically run models. We try to kind of unify the interface to different models so that it's easy to pick different models to run, but also that you can quite easily start 3 different models and then actually start to compare them or actually couple them in some way, do a comparison, do data simulation, for instance, also something you could do here, although you, of course, still need to the whole algorithm for data simulation. But in principle, since it's very easy here to start a bunch of models, let's say, and run them and play with them, it's actually very easy to kind of experiment with the coupling in a way. So when we started this project, we quickly got around to getting all these models in our system, and then we actually found out that one of the common problems that hydrologists were facing was how to get forcing into their models. So here you can see forcing, so for instance, reanalysis data has to be converted to the model-specific input format, which could be anything. Hopefully, it's an etcdf file, but sometimes it's CSV files, Excel sheets. We've seen pretty much everything by now. And then in the end, a hydrograph comes out, which is the common plot used in hydrology. So what we actually found out that there's quite a few steps involved in this pre-processing, and people had been putting this in bash scripts somewhere on their hard drive that they forgot about, and this was actually really hindering the way people were able to use different forcings and also each other's models. So on the bottom you can actually see a small pipeline of all the steps required, so regridding, selection, derivation, converting to a model-specific format. As you actually see this also, well, when coupling different models, you get exactly the same problems. But in this case, it's kind of coupling a data set to a model in a way. So for our system, actually, we started using a climate model tool. So it's called ENES-RI tool. It's the Earth System Model evaluation tool, which is actually used to produce analysis and plots and diagnostics of climate models. So, for instance, the CMIP 5 and 6 intercomparison projects. So we actually found out we were already working on this tool for a few climate projects, and then we actually figured out that the output analysis of a climate model is pretty equal to the input processing needed by a hydrology project. So we actually reused this tool for hydrology, where we use the tool to actually do the regridding and the derivation and converting to model-specific formats for us. And then the nice thing is that we then suddenly support quite a few climate data sets, kind of out of the box, and also as part of this community. So, for instance, all the CMIP 5 and CMIP 6 models, also ERA interim, ERA 5, and there's actually continuously more observational data sets, as they're called in ENES-RI tool, added that we can then also make use of, which is really nice. Good reuse of data and effort and software, we think. And then this also allows us to quite easily support different hydrological models, no matter how quirky or odd their input processing is. So now we tackle this problem of getting forcing into our models. So how about the actual coupling, right? So what kind of interface do we use to talk to the models within our system? So we actually found the basic model interface, which you may have heard at previous iterations of this workshop of as well. So it's from the CSDMS community, and it's actually an attempt at building the most simplest of model interfaces, so that it actually becomes quite easy both to add a model to add this BMI interface to your model, but also then to use it in a framework. what I really like about the basic model interface is that you can kind of agree to disagree about what the best framework is. So I'll show a picture next of what our system looks like, a few slides down. But you don't need to agree on this, right? So the CSDMS people use sometimes use a slightly different variant, and you can actually build a whole new framework, but then reuse this coupling, right? So then hopefully this will allow other people to reuse either these couplings or these frameworks without having to continuously build this interface. And as you can see, it's a very simple interface. So there's a initialize and update, which is basically do a step of the model and initialize the model. And then there's some functions for getting the type of grid supported by this model, the units that you can ask, and then the get value and set value are basically the basic functions that they use to actually get values out of this. As you can see, the models are very much treated as libraries. So there's basically the whatever's on top is in the lead of actually doing steps and deciding what goes where. Here's a picture, it's a bit cropped, at least on my screen, where you can actually see this in practice, right? So there's this initialize function, there's the update, which actually runs the model, and then get and set value allow you actually to talk to this model. Since we do this in this interactive Python methods frame setting, it's actually quite nice that a scientist can just run a model a couple of time steps and then actually start kind of investigating what's in the model without having to write this all to disk. You can actually also influence a model, right? So both if you're really trying to either make or debug or set up some kind of coupling system, but also just to do kind of quick what-if scenarios, right? So you can kind of start pushing at your model quite quickly with these interfaces. And then in the end, there's finalize. There's a quite extensive number of these metadata functions in BMI, where you can actually see what kind of grid is supported and get all the information that you need to know what kind of grid you're talking to, which is of course very important. Right. So now we have all these models. We know how to get data into them. So now, how do we actually run them all? What we actually figured out is that since we have so many different modeling languages and modeling frameworks or libraries used in that we actually thought it would be pretty much impossible to try to get a software environment on any machine that actually supports more than a few models, and hopefully we want to get up to 20, 30, 40 models.
Niels?
Yeah.
2 minutes.
Sure. Thank you. So what we actually do is we use container technology. So in this case, Docker. We also support Singularity. And then we actually put the models into this container environment, including a BMI interface. And then we use something called gRPC, which is a Google invention for talking to remote processes to actually then talk to this container. So then it just kind of turns the model into a service in a way. And then again, using BMI and from Jupyter or some other Python environment, we actually talk to these models. And you can see a very small snippet here of how to start and run a model. You can see that we kind of hit all the creation of these containers to a simple creator function. And then you can use this model as though it was just available to you in Python, which we think is a really nice intuitive way of interfacing to models and will allow us to actually build these more advanced couplings and switch out different models quite quickly. Yes, be in touch. So we're really trying to build a community here in eWaterCycle, which is also why a lot of the parts we use are kind of useful by themselves. So it's not like we don't have this big platform and you have to use the whole thing. I really try to contribute in different ways, and also have a look at BMI if you're interested. That's it. Thank you.